Okay, so thanks everybody for joining us here. It's been a couple weeks and I was relaying to the two here in the room that we've been off a few weeks because of I travel out to New Mexico 2 weekends ago. That we've kind of overlapped, or we weren't for sure. I wasn't for sure if I'd be back. That the last week was just after, and we weren't sure how recovery would went. But all the balloon stuff went well. And we're, at least most of it went well. Our big thing we still need to work on, but everything else went really well. So that's really pleased that that was the only thing that went bad. But for today, completely different thing, not balloons, and much higher in the atmosphere or kind of in space. We'll hear from Dr. Machete, who joins us from Botswana, and it's Dr. Lenny Smith's postdoc student, yes?
Wow, Fulbright fellow.
Fulbright fellow, sorry. Did not mean to gloss over that. Yeah,
But
Fulbright
also
fellow.
former graduate student,
Okay. There you go.
Commonwealth graduate student.
Yeah.
Okay, there you go. So yeah, we'll hear on a kind of more statistical, as I was kind of talking about this in our meeting, more of a statistical kind of approach to thinking about solar activity and solar storms and things like that. So, without further ado, I'll turn it over to you.
Okay. Yeah. Am I speaking into this?
Yeah.
Oh,
So,
okay.
very informal. Feel free to just sit.
That's fine.
Yeah, that's the microphone for people who are online.
Yeah. Okay. I mean, it would have been great to see whoever is attending online, how they look like, what they do. But
Yeah.
yeah. So I am from Botswana. I'm a Fulbright fellow here. On sabbatical. I'm here until end of December.
Okay.
And then I'll be heading back home.
Okay.
So the first few months I spent time looking at this because Eleni had told me there is a group that does stuff like this, and I sort of found it interesting to do something in it.
Yeah.
In the context of my toolboxes. So yeah, so I thought, so today's presentation is a probabilistic framework for forecasting solar activity. So, I mean, I've seen what people do. People do forecasts of stuff in this context using what they call deep learning tools, and they have done a few things. And we thought we could put something together that people could actually think it's useful, maybe could help them tackle problems within this context. So
let me know when you want me to advance.
yeah, we can move to the next page.
See if that works.
So if we're going to set this up, one question is, what is the nature of the dynamics of the thing we're looking at? And we're taken to that paper by Yule in 1927, who was looking at sunspots data and trying to understand what these are, using some autoregressive models and quite some deep analysis. And so the work is published in the Proceedings of, I think, National Academy of Science or something, I can't remember. So yeah, so he considered more like 3 decades of data. This is quite a long data set. And one the key conclusions he comes to is that the motion displays periodic movement of randomly varying periods. So you can't really pin down the specific period, but you can just know in general it's about this length, it's about 11, it's about 10, 9, sort of just vary. And where it varies, it's like it's a pendulum subjected to random impulses. And you know what that means. I mean, if you're putting, it's like the forcing term on the other side keeps on changing in a random way. And that suggests it's changing in a nonlinear way if you're really putting these random impulses like that. And the other finding he makes that there is an element of unpredictability that is rapidly increasing with time. So to understand what that means, I mean, I think looking at this in 1927, I don't think he knew more of what that really meant. I mean, you look at, it was until 1963, move to the next page there, that so we sort of conclude from those statements, we can say the dynamics there are nonlinear, and more than that, we dare say chaotic, but really chaotic is a way of modeling rather than really. It's our perception in terms of what model do you think is most relevant to the dynamics under study. But you see, that was still at infancy, that area was still young at the time. Poincaré's work on celestial mechanics was still probably not widely publicized, which he had done until 1899, where he spoke about this idea of a recurrence, that you get a system will sort of come close to the same dynamics. The periods will be changing from time to time, but sort of similar. And there'll be infinitely sort of many periods in their context. And then we came to Lorentz butterfly effect in 1963, where he's claimed that a tornado, a butterfly flapping its wings in Brazil will trigger a tornado in Texas. So there's the idea of rapidly growing unpredictability, that while you think things are happening in Brazil, their effect is going to be quite elsewhere, and the unpredictability that grows. In the language of the chaos theory, they say initial uncertainties grow exponential with time. And so, in light of this, let's move to the next page. How do we really evaluate models? How should we really evaluate models in this context? If the dynamics are nonlinear, and we dare say if the dynamics are chaotic, how do we evaluate them? I mean, people have used the root mean squared error quite a lot. But you look at that paper by Machete in 1999, it shows that when the dynamics are nonlinear, the root mean squared error is really a bad metric to use. It's a really bad metric to use. So we go to the next page where we'll show the graphs from there. So looking at that system there, the logistic map, that map was sort of made famous in 1976 by Lord Robert May of, I think he's in the UK. Of course, that's the only place where people are called lords. So there's a parameter A in that model that you see there, and A equals to 2 there is what they looked at. A equals to 2, the dynamics are chaotic, and they know the statistical dynamics in a closed form, the distribution of the dynamics in a closed form, so that they could actually work out numerically quite well, almost precisely what it is. So when they check how the best model fits there to sort of trying to estimate the correct parameter, when you do the RMS error, as you increase the noise in the data, it gets worse and worse. I mean, you can see the estimate gets worse and worse, far away from the true value of A. So which simply says the root mean squared error, especially when it's noisy and the system is nonlinear and chaotic, is a bad metric to use.
And that's with how much data?
Huh?
That's with how much data?
I think it's quite it's varying, but quite a lot, even with infinite amount of data.
So this was an infinite amount of data.
With infinite amount of data.
It still gives you the wrong answer.
So you don't get better because of doing more and more observations. So, and we know that in our context here, we don't know the exact values for the observations. So this is really the context where we really need to rethink of how we really evaluate these, how our models are performing. And let's move to the next point there. And so that sort of shows those are the details of the results. So you can see the dark thing there coming at the bottom there. So top there, that's what they call the buffer, the transition sequence for different parameters, and you can see at the maximum where A is equal to 2. So you have windows where it's periodic, but overall where you see it's shaded there, that's the system is chaotic in those areas. We won't say, well, I mean, we sort of won't take it for granted that you sort of understand. We'll not explain what chaotic means. But you can see there when we move into that region there, so you can see the RMS going astray in predicting the parameter values for different noise levels. And the maximum likelihood estimate is the one that actually does better than the other stuff. So this is where you are fitting a distribution around the noise, rather than, I mean, around the observations, rather than doing the RMS approach. So you can see that we really need, if we are going to understand this better, we need a probabilistic approach rather than to just go with the RMS error that is commonly used around. So let's move to the next page. And now what we get is what people make, how forecasts are made. We'll see this in more detail. But in forecasting solar activity, people tend to give point forecasts. They don't give distributions like we were suggesting is the way to go. But that's still fine. But we could do better. It is still fine. We can work with the best. We can make the best of what we have. And now the question is, how do we move from point forecast to predictive distributions? How can we change this to distributions? So this is really the main point of the presentation, is how do we move from these, and how do we evaluate those? How do we check how well we're doing? We'll not talk too much about Low-Vol's equation there, but that's another approach in the context of chaotic dynamics. So that's sort of, it shows how the initial uncertainty grow with time, how it's just the model for this. So let's move to the next page there. Yeah, so when you have point forecast, we can have a single point forecast. We can put a Gaussian distribution around it. So you can see the top graph there that we have. So you see a standard Gaussian there that we use. So we sort of say we dress it up with a Gaussian distribution, this single point. We can do that. And now the variables we're looking at are non-negative. Sunspots data, sunspots is non-negative. And the variable we're going to look at after F10.7 is non-negative as well. So thinking Gaussian in its simple sense will not work. You have to cut off the negative bit. So that's why we talk of the truncated Gaussian here. And the question is, how does it work? We compare this with another method where we look at the distribution of errors, an archive of one-step errors from forecasting the given variable, and say, can we exploit this performance of forecast errors in the past to get a fairly good estimate, and rather than just go with the Gaussian? I mean, the Gaussian is sort of the natural approach to use by many statistics. I mean, by many people. Statistics seems to really rely a lot on the Gaussian distribution, so that you cannot move any further before you address the Gaussian. So let's move to the next. So we are going to compare those two approaches, which is the Gaussian distribution method and what we call the error distribution method, where we look at the errors in the past and put them around the observations in some way. And so we compare them with a baseline. The baseline is, we just look at the current observation and use it as a forecast for the next foreseeable, for whatever time horizon we're looking at. So just look at, so we just assume the dynamics will be as they are today. That's the persistent forecast. Or we can look at the climatological distribution, it's the distribution of our past as we have it at a given time. And you could use that and say, in the worst case scenario, how do we, if you can't beat that distribution, then you are not fit purpose. alternatively, if you can't do the persistent forecast, which is like the poor man's forecast, then your model has no value. I mean, if somebody can just do this and beat you. So then we'll look at the variable of interest, which is the. So we'll look at this within the high solar activity and low solar activity regions. Now we'll go to the variable of the next page. So the question is, how do you discriminate between competing models of solar activity? Now there are different. So given those models, given competing models, how do you compare them? So in the probabilistic framework for probabilistic forecast, there are different scoring rules, as they call them, for really evaluating these models. And we're sort of spoiled for choice. We need to pick the right one. And the choice depends on the decision question at hand in general. There is no universal. But we will suggest that the one similar to maximum likelihood kind of, the logarithm scoring rule or the ignorance score, in the absence of any really information of what the real purpose is probably the simple go-to scoring rule that you can use, scoring function that you can use, or loss function. I mean, I think in the engineering people talk more about loss functions. So what loss function can we use? And we're saying here we can use the log score, which is the ignorance score. So move to the next page there. And its preference is that it is slow. One of the good things about it is that it doesn't require a lot. There is not a lot of integration to make. It's just local. You just evaluate it at the observation, which makes it easy to use. And it's also related. You can relate it to investment returns. If you were to put investment in with some returns in some whatever portfolio, I mean, some investments framework, you can sort of, you can know what it means in terms of the money you would make if you were to invest that money where there are some returns, annual returns or daily returns. It depends on your time frame. And the idea is, if you think your forecast has value, can you put your money on it? And if you're going to put your money and compete with someone else, say somebody has the persistent forecast, and say, let's all bet our money on it, and let's see if you think your forecast has value, I'll put my money using the persistent forecast, and you put your money using your whatever model you're using to your forecast model, and let's see who makes money. And you're going to pay me if in the long run my model beats you. So that's the idea, that so you can sort of justify it in that sense, that it makes sense. If you have something is great, you can put your money on it. And this shows you it's an idea of arguing how you can put your money on it. So now we move to the next. So we'll look at, in this setup, we look at NOAA forecasts, which are, they issue 3 types of forecasts. They've issued 3 hourly forecasts, which we are not going to look at. These go up to lead times of 3 days. And they are 3 hourly. Every 3 hours, they issue new forecasts up to 3 days. And they also do the 1 to 27 day lead times, where these forecasts are given on a daily basis. And they all call this a 27-day outlook. So within this, they have different variables that they give for these. These are given on a weekly basis. And in the archives, they have these coming from all the way from 1997 up to now. So the information is available at this web, the Space Weather Prediction Center. So let's move to the next. So this 27-day outlook, I understand, are produced from Boulder, Colorado, jointly with between those 2 centers, NOAA and the Air Force Weather Agency. And there is no real information of how they produce the forecasts, except that they say They are based on precursor methods, neural network, spectral methods, even odd methods. These are like the main methods that they use, and they say they lay the greatest weight on the precursor methods. I don't know what these methods are.
Do you know what the even odd behavior is?
I don't know what that is.
I don't know if it's a sum thing or a stats thing.
Oh, okay.
I don't know. I don't,
Yeah.
on even days, on the Thursday effect.
Yeah.
I've never heard of that.
So what they say is that these precursor methods are based on the forecasts are based on persistence of patterns of solar activity or geophysical activity from 27-day rotation to the next, 27-day rotation to the next. So somehow I think they assume the persistence of the cycle and use that cycle to sort of make the forecast. It's not the persistence as we have, it's not our simple persistence like we have done. But they do know that the recurrence, while their models are based on this aspect of recurrence, the recurrence varies a lot throughout the solar cycle. I mean, Lorenz, when he presented his work on chaos several years ago, one of the things he argued for was that if we don't have any models, we can wait for what you call the analogs. And this seems to me like the method of analogs, where you sort of look for trajectories and that you can use from the data, patterns from data that you think are consistent with the dynamics, and use them to make the forecast. So this seems a lot like something like that. Similar, I mean, not maybe quite exact. And they use what they call the extended solar cycle, where they sort of look at the declining phase and then extend it into the next day, 27-day period. And that's how they produce their forecast. Yeah. So, yeah, we can move to the next page. So they look at different variables in terms of those outputs. So there is the F10.7 radio flux. And there is also the there also the planetary A index. I don't know the details of what these are. I mean, I hope to learn more about what they are in terms of substantial, what do they really mean? And the largest expected KP index. So those are the three main variables that they use to make the forecast, to produce forecast for. And the formation methods are used for both the F10.7 and the sunspots data. So the key things for those methods, variables, are the F10.7 and the sunspot number.
Do you really care about F10.7?
I don't.
So is this really about predicting F10.7, or is it about something else?
I think it's more about predicting the dynamics in the solar activity. And what you notice that if you look at those three variables, what's common about them is that they're all of them are non-negative. So, but the ideas we are putting forth, we don't really care. The F10.7 is just probably one of those without not much work has been done on this in terms of looking at forecast and its dynamics. The sunspot data has been heavily studied.
Yeah.
So we just chose the one sort of the road less traveled. So we can move to the next page. So I'm not sure if I should really tell people in this audience what this is. I mean, they probably know more about it than me. But that is it about so this is an index of, so the F10.7 is an index of solar activity. And it can be used to sort of capture what's going on in solar activity, especially if we are interested in the density of near-Earth orbits. It's like a good input if you want to understand what's going on there, and you can use it as input to sort of estimate density and understand things about the drag on the motion of satellites. So this is one of the reasons why this might be useful to people who are looking at satellites. But any further in terms of if impact in terms of what's going on in the Earth would be interesting to learn. So we can move to the next one. So here they are sort of give the time series of this index. You can see that it has that sort of. Hey, why has the color changed?
It's from the projector.
Projector is a little.
Okay. I mean, of course, the color isn't important. So we show these from the data from the archives. So what they issue is what NOAA issues is these weekly reports. And these forecasts are issued in weekly reports that are issued every Monday for the next that's forecast or outlook, as they put it, for the next 27 days. Every Monday they issue a new one. And they have an archive of these dating back to 1997. So we really must obtain data from these archives from 1997 to sort of look at this, what's going on. And that is the cycle we're looking at. But we're looking at that on a daily basis. That is really the main thing we're looking at, and this is on a daily basis. And you can see the highly oscillatory, about the peaks, it's highly oscillatory. And that the region we'll call the region of high solar activity. And toward the troughs, at the bottom there, you see there is less oscillation. Those are regions of low solar activity as we perceive them. And so in terms of high and low, we sort of distinguish between these two regions.
So the zeros, those are presumably just missing data. Or
Yeah, those must be some.
So I'm happy to believe those are anomalous. What about the spikes? Like that one that goes up to 300, or are those like really big bursts, or?
I didn't know what the reason for the best is. I mean, I have no clue why.
Is that just the day you don't want to be on the space station, or?
Or just some problem with the data. I mean, the observations are measured from in Canada. Some observation center in Canada. So, and they say they revise these. I mean, they always say you shouldn't use these observations as they are. You have to wait until they are revised. I mean, I don't know why we should. It makes sense to use what was used when the forecasts were issued.
But if they, do you know what they do when they're evaluating their forecast? Because if you have a 300 in there under RMS error, then whatever model did that, whatever model just happened to have the lowest forecast values, so they get a really big hit.
Yeah, I mean, I haven't seen the evaluations of their models, to be honest.
Yeah, no, I couldn't find anything on the.
Yeah,
numbers you said.
I haven't seen any evaluations of their models. I mean,
No, maybe you can ask them.
Is there a possibility that the points which we are seeing like very low values are like these that they had fault, or like the system was at fault or something like that?
Yeah, I think the zeros are just failures to record a value, so they're literally put in as zero, as opposed to not a number. So those people usually take out, but if it's not obvious whether that 300 is a really noisy day or whether it was some other machine glitch, and those can really kill.
yeah, if a machine malfunctioned on the day.
Yeah. Of the day.
Yeah, so it might be something like that. So I think let's see the next slide there. Yeah. So there I show the one-step errors for their forecast. So tau equals to 1 day. That 1 day is 1 day ahead. So you can see. So that is a time series of the one-step forecast errors from 1997 all the way up to 2022. And that's for the NOAA forecasts. And for the persistent model, our persistence, where you assume nothing changes. So at a lead time of 1 day, so that's how the errors look like. And you can see the periods of high solar activity, the errors are bigger there. And the quieter areas, the old areas are the errors are smaller. which sort of makes sense. That, yeah, so we have that variation in predictability there. Now let's move to the next. So that's for 6 days ahead. So we just showed for no good reason. I mean, we simply picked 1 day ahead, makes sense to look at. But also we show the 6 days ahead. So you can see the errors are bigger the further ahead you are. But you can see one interesting thing is that the persistent forecast seems to compete fairly well with the NOAA forecast. At 6 days ahead. I mean, I don't know how much changes within that sort of time period. Probably that is the period where not much has changed, so that there is not much value in doing anything sophisticated. You may just as well within those time scales just issue the persistent forecast and wait for where things really change.
Is the scale the same as the last graph?
Huh?
Can we go back one? Yeah, so the scale, the vertical scale is the same.
Oh, I think it has changed. Let's compare. How has
Just
it?
the size of the scale.
Yeah, the same. It's the same. Yeah,
Right.
yeah. Okay. Yeah. So so you can see that in terms of forecast distributions, I think. So we show this at 4 days ahead. So on the left there, that's distributions during periods of low solar activity. So those are based on, yeah, I'm not sure which method there, but but you can see that the periods of low solar activity, the forecast distributions are much sharper. And during the periods of high solar activity, they are wider. They are much wider, which sort of, it makes sense. It makes sense that during periods of high solar activity, the distributions are wider. But you can see the climatological distribution there, that sort of green, yellowish green graph. And if your forecast distribution is not sharper than the climatological distribution, it probably doesn't have much value. You really want your forecast distribution to be sharper than that. So if you are not sharper than that, I mean, your uncertainty is just about as good as the climatology. And that really may put questions on your forecast, on the value of your forecast. Yeah, so I think we can move to the next slide there, where, I mean, my glasses let me down. I lost my good glasses earlier this year. And so you can see here that we have this. So here we compare these two approaches. I mean, you can see on the left there is the training period, and on the right is the testing period. So we sort of look at the performance of these two testing and training. And we compare these during periods of low solar activity and high solar activity. And you can see both methods know about this comparison of NOAA versus climatology at the top. I mean, at the bottom and persistence at the top. And you can see that in the training period, persistence, and NOAA doesn't really do better than persistence, up to about 5 or 6 days there. Please consider that graph you saw there. So we can see that this is not quite an artifact of our method. That NOAA doesn't do much better up to 5 or 6 days. In both periods, I mean in both.
So can you tell us again what's the blue line and what's the red dashed line?
So
NOAA.
So the red dashed line is low solar activity period. So we sort of split this.
So it's NOAA versus persistence during low activity.
Yeah. So when the score is less than 0, NOAA is better. When it is positive, the persistence is better.
And when it's 0, they're about the same.
Huh?
And when it's 0, they are about
When
the
it's 0, they are about the same. So we compare periods of high solar activity and periods of low solar activity. And you can see there that so NOAA during periods of high solar activity, NOAA gets better beyond I think 5 days. That's when, I think when beyond 5 days, that's where existence sort of is not so available. And it keeps on like that up to about, I think 25 or so. Where now I think your model begins to lose speed. It is about as good as just using persistence again. So this is the key thing. So we see this in the training period, and also sort of in the testing period. I mean, maybe not so strongly here. I mean, I don't know. I mean, so this is the high solar activity. You can see that it's marginally better. It is, or is it better? Yeah, it is. It is marginally better in high periods of high solar activity. And you can see that in low solar activity, usually you can't say who is better. I mean, it's about it. We might as well just use the persistence than try to use some skill. As long as we know we are doing our observation is at a period of low solar activity. Now, NOAA-based climatology has now in every instance. I mean, in terms of low solar activity, high solar activity, it makes no sense to do climatology. But so the real test, the real competitor is the persistence forecast. So let's look at the next graph, which is about I think, comparing these methods. Yeah. So here we sort of compare the error distribution method versus the Gaussian method. So I think with those graphs there that you show, we're using the error distribution method. And the question is, which of these would do well? So you can see the error during periods of high solar activity in this, the error distribution method and what there isn't much difference between that with the Gaussian method. And you can see, whereas during periods of low solar activity, the error distribution method does better than the Gaussian method. So I think the graph I should have shown would be performance of those methods when you use the Gaussian distribution. And I think what you're going to see here is that the NOAA forecast, we're going to far out. I mean, I'm not sure what we're going to see. I mean, I should actually get a few of those graphs and find out what they are. But what we see is that our error distribution methods outperforms just the traditional Gaussian method. It's not traditional in the sense that we have done the truncation. Otherwise, it is the Gaussian methods, nonetheless. And similarly here, how the difference between these two is. So this is the testing period. This is the testing game. So this side is NOAA and this side is Gaussian. Yeah, I mean it's based on Gaussian. So you can see this side. I mean the same sort of story here. That's going on. Yeah. So you can't really take in between. So by the low solar activity period, that's where our method it does better than the error distribution method. I don't know which one. We should really own any of these methods. Yeah, but the error distribution method does better than the Gaussian. So overall, we see that at worst, the error distribution method performs just about as good as the Gaussian method. Otherwise, it would do better than the Gaussian method, the Gaussian distribution method.
And then what does 0.5 mean on this scale?
This is in B. So 0.5, this is B. This is in terms of logs. So
So it's
like
half a bit.
Huh?
So it's half a bit.
half a bit, yeah.
Square root of 2, right? So
Yeah.
that means it's putting 40% more probability on the thing that actually happened. Right? 1.4. So 40% more probability. So it's really a half it's a number that means something and it's big. I mean, if you it's not like some weird metric that just gives you a rank ordering, but where the axis doesn't mean anything. 0 means log, log of 1.
Yeah.
It's the same. And a half means square root of 2 more probability.
Yeah, I mean, it's like 0.5 bit of information.
Mhm.
So we can move to the next page there, which is, yeah, so, I mean, this is no more than what we've already covered. But the error distribution methods appear. Sorry for that, field distribution that are sharper than those obtained by a recursive distribution method. And periods of isolation activity gave mixed result at different lead times for the two methods, meaning you can take much between the two methods during periods of high solar activity. And so but periods of low solar activity, the error distribution method is better than the Gaussian method and distribution method. And based on the error distribution method, no forecast will found to outperform the same forecast during periods of high solar activity. Of course, only after like 5 days ahead, new times. And during periods of low solar activity, no forecast gave mixed results. It's hard to say. So the point, the areas where we really, I mean, I don't know if it's really important to worry about periods of low solar activity in terms of this forecast. Can you settle like, yeah, okay, those we can get with the persistence, that's fine. And there's no need to develop models more seriously for that. I don't know in terms of application for use. Because it really meant that when it's quiet. We can say when it's quieter, maybe there isn't much to do. So there isn't much activity. So why worry? Now, looking ahead.
Actually, could we stay on that one for just a minute?
Huh?
So I guess maybe in terms of forecasting, there isn't much to do, but I mean, if you really don't care about forecasting at all, but you just want to see how well you can simulate the sun or wind patterns for your balloon tracks or whatever it is, then even in periods of low activity, just because the forecast distribution is narrow doesn't mean it's going to be log P is going to be high, right? I mean, it could be a narrow one, a very narrow one, and a not so narrow one. They could have really different information content. I mean, you could tell you, I mean, if your model, what am I trying to say? I'm trying to say you're trying to distinguish a model, whether a model is good in high solar activity means the distribution is going to be pretty wide and all the models have to give wide distribution.
Yeah.
But if you're good during low solar activity, then you're not just giving a narrower one, but the model has to be sort of have a chance of getting the right narrower one. So I agree persistence is going to look a lot better, but it would seem to me it would be a good place to test your models.
It's a good place.
It could be a good place.
Oh, yeah.
You were sort of saying nobody cares. I said, well, I may not care if I'm in the space station, but if I'm trying to develop my model of the sun, I might care a lot because that may tell me a lot about how I do about the physics in my model. It's using the statistics to try to see whether or not you have the physics right. I mean, the statistics for the statistics, maybe I don't care. But if you're using the statistics to see if you have the physics right, I would just think I wouldn't throw away the low activity quite as fast as you do. I think it could be interesting to be in either place.
We may need to sort of do well in periods of low solar activity.
Or if we don't, we may be able to fix the model. Whereas in periods of high solar activity, it may be so volatile. You know, if you could, it's hard to predict turbulence. But if you can't predict laminar flow, you know there's something wrong with your model. You might fix it to get nice smooth flow first, and then worry about turbulence.
Okay.
Maybe.
Yeah, makes sense. Yeah, I'm agree with that. Yeah. So I mean, these are just it's really great. Yes.
And now you're going to say what I just asked, right? Sorry about that.
So like you say, maybe we need to develop our models for periods of low solar activity, and they find models that do really well in those periods. Overall, can we improve our models any better? I mean, do we need a better better baseline. To obviously, if there's any model, I mean, so when your forecast do well, any model that is going to do better and to be allowed should be to the lower forecast. So whoever is doing best at the moment is the man to beat. So explore impact modeling. I mean, I'm interested in exploring impact modeling and where probability forecast can be taken as inputs to inform decision making. Even if it's not just decision making or even just to have model development, and that would be great. If it's not impact modeling.
So does the Botswana, I can't remember the name of the climate, but does the place you work when you're not here? Does it do space weather forecasts? Is it interested in those impacts or is it only interested in?
And then my interest probably can, yeah. They haven't done anything of that stuff. So my question is, in terms of space weather, which regions of the world are really affected by this? And I mean, I saw that it shows that things like GPS are affected by these.
How far south is Botswana?
Huh?
How far south of the equator is Botswana?
I
Right,
can't remember now. I mean,
right below the
It's,
equator.
Right,
it's 26-degree latitudes or something
26, so it's like Florida, but the other way.
Mm,
to.
Yeah.
So it's not that close to the pole.
no, no, of course.
I'm just wondering how close it was to,
Yeah, I think it's from 26 degrees south. I'm not sure up to. Is it up to 40 or something like that?
yeah, okay,
In terms of latitude.
wider than Florida.
Huh?
Wider than Florida.
Yeah.
Yeah, why-
Florida to here,
Yeah.
the south.
Yeah. So in that sense, I don't know. So I don't know how GPS gets affected. Does it depend on where you are? Like can Botswana could we be affected or less affected by what's going on in the solar activity?
Mm.
And if we do get affected, then it makes sense for us to be heavily interested in this.
Mm.
So those are things I need to do. So other things would be to look at the other things. I mean, it depends to what interest, to what extent they inform modeling, but I'm sure they do. And this could actually us into having solar storms and associated terrestrial impacts as we move into the other indices and different levels of severity. And the choice of an appropriate scoring rule depending on the probability scoring or whichever. I mean, I'm not sure whether we should be thinking of utility theory, which is some other aspect when you think about impacts, not merely thinking about scoring rules, but what is the best function to use beyond what's there in the literature in terms of scoring rules. So those sort of issues, I think they would be interesting to explore. But anyway, I'm only here until.
Well, then we can continue working when you go back.
Huh?
Maybe we can continue working when you go back.
Yeah, but surely if to the extent that these affect us directly or indirectly in Botswana, this will be interesting to Botswana. As long as they will affect us somehow, not mainly health. It shouldn't just be of value outside, as long as it also has local value, then.
And would that be the institute you work for? Are they the institute that you work for?
Yeah.
With, for whatever.
Yeah.
Are they in charge of all those kinds of environmental issues or more weather, terrestrial weather? If it is important in
It's an Institute
Botswana,
for Technology Research.
what?
They have Institute for Technology Research. So we have different aspects. We have climate, environment, we have natural resources, we have also electronics communications, where they're interested in technology in general. They have IT as well. But there's one section that is technologies, there's another section that is natural resources. I mean, the natural resources section. But they always worry about the silos, as they call it. That people are working in silos, they should work together. But they are interested in technology questions. Especially if it's deemed to be at the cutting edge, I think they will be interested.
Thank you.
So, yeah, that's it. Hopefully I haven't gone beyond the time of the correction. I think that's all.
Oh, perfect.
There we got a few minutes, 30 minutes. Yeah, thank you very much.
Okay, my pleasure.
Let's see, if there's any. Nothing in the chat so far, but anybody who's online, any questions? We've kind of started questions here.
Yeah, yeah, I came in, but we're hearing the NOAA, the NOAA.
Yeah.
Yeah, so is that a model that you built or
Oh, no, it's a weather center in the US.
oh okay.
They call it National Oceanic
Atmosphere.
and Atmospheric
Association.
Administration.
Could we see that?
Yes, you're talking about.
And while you were comparing it to I heard about the climate, what's it called?
Climatology,
Yeah, but there was a second one that you were comparing.
persistence.
The persistence. So that one was what you.
Yeah, just saying no change.
Oh, okay.
Yeah, this is.
So is it different from the one that you look at? Is it different from the one that you look at? The one
Next
we
one.
use- Oh, okay, okay. But I remember the one that we were using to monitor
Yeah, so the data
hurricanes.
is sort of from there.
The one that we were using to monitor the hurricanes. It looks like this.
Oh, no, that's, yeah, this is more the A and that is more the O.
Oh,
That's the National Hurricane Center in Miami, and this is in Boulder, I think.
yeah.
And where are we now? What is,
What's that? So this is, 10.7.
Yeah.
and that date? What are the
We are
dates?
down there.
So this was the latest,
Yeah.
Yeah, yeah.
the current forecast.
So is that sorry, how long is the x-axis?
This looks like it's 2019, and
Mhm.
that's 2000.
Right, okay, good. So we're just not dismissing 3 years.
Yeah,
Mhm.
yeah.
So there's a maximum around 24, around 14, or a maximum around, yeah, around 1 or 2, around 14. And then again around presumably 26, 25.
Yeah. Which,
There was a threat warning axis.
And it's live image.
Looks like a pretty quiet sun.
yeah. There was a graph.
If it was up to date, I would have been interested in, let's say, how things changed during the eclipse. No,
During,
the recent eclipse. You know, there was a recent eclipse.
So presumably.
I
what
heard
happened
about
during- He was there.
What's that?
The recent eclipse.
Yes.
Yeah, I was looking at the data. If it was really up to date, like I would have actually been interested in how things actually changed during the eclipse.
Does radio flux change during the eclipse?
Oh, that's a good question. I'm not sure. We haven't had anybody look into that. I guess it's gonna be a very.
I guess it has to. Yeah, but yeah. Oh, I guess it's probably because whether the shadow hits the poles or something.
Yeah, yeah, it's gonna be a very localized effect.
yeah. Whereas this is not local, it's not a local index.
Yeah.
It's a
Yeah,
global
yeah,
measure. Oh,
Yeah.
It would be cool if the shadow, sort of a polar eclipse, was noticeable in
Yeah.
radio transmissions
Yeah.
in the tropics.
Yeah.
But that's, so there's one on forecast verification. Can you,
What's that?
under, if you go straight down, yeah, and up about 5, forecast verification. As opposed to evaluation. Forecast observations. So what would you care about? Or maybe not for balloons, but if you put on all your hats at once, and I think there's an extra hat in the storage unit, but I don't think that hat is mine. Maybe you're trying to get rid of some of yours, but I mean, in terms of people here in general in space weather, what sorts of things might they be most interested in?
I think I might be, not to call him out, but Dr. Bailey, if you're on and hear us, maybe that's the question for you.
It's on mute.
It might be muted.
Yep, sorry about that. Could you tell me that question again?
I was just in terms of, there are lots of indices and various things that Reason and I really don't know who cares about. I'm just wondering which indices or which empirical phenomena that people forecast would people at VT, space at VT, what would we really care about? Is that a reasonable thing to
Yeah,
say?
yeah, yeah.
Yeah, it's different people, different things, the applications are different. For me, it's always F-10-7 and AP. Although I only sometimes need predictions, but every now and then I do. But I'll bet you Mike and Joe would say DST or something else. I don't know if either of them are there. It's application dependent.
Yeah, DST, and it was a.
Thank you.
Hmm?
People don't pay
Yeah, I guess the question is that we're really not trying to get to predictions so much as we're trying to evaluate models and using predictions as sort of one of the ways to evaluate them. So the question of what you'd really like to be able to model better is sort of the same for us. DST real time.
Mm.
Yeah.
The graph is up now. I don't know if you can see it, Scott.
Yeah, I see it.
Yeah, this is one of the indices. It's generally right that you can see for solar storms and things like that. And yeah, when we look at it for super dark, a lot of times
Is it related to the KP index?
it's close. Yeah,
Close.
They're closely related. Yeah.
Yeah, thanks. We'll take a look, Scott.
Sure.
Yeah. Otherwise, for super dark type stuff, we also look at kind of the solar wind parameters that are going on in real time. A lot of times, what the IMF, especially this BZ parameter, what's going on, and as well too.
Is that some vertical magnetic field? What's BZ?
Yeah. So this is the magnetic field parameters of what's the interplanetary magnetic field. So what the sun is launching off, and then it interacts with Earth's magnetic field, kind of thing, right? Because that's the strong driver on how our Earth's magnetic field, all reconfigures when something, hits it. So.
Thanks.
Yeah.
I think if you're pursuing this further, some of the, there's one is just, scoring different days and how it works. But when the change is big and over a short time, those are the things that are most important to predict that would help lots of people in different communities. I don't know if there's a way to consider the scoring where it is kind of based on the nature of the change, if that makes sense.
Kind of based on the what?
The nature of the change, right? So like if you take this further, I would think one of the biggest applications would be if you could predict when one day or over a certain few hours, all of a sudden the X-rays, right, what F-10-7 is indicative of, increases sharply over a short time, right? That would tell you that you can't depend on GPS for a while.
Right.
So it's not just, how well is the model working, but how well it's working on changes of a certain time scale.
So I guess what we'd see there is, you might see a fairly, I know you can't see me, but I'm going to raise my hand anyway. In case we would see this sort of narrow predictive distribution, and then all of a sudden it would start to get really wide if there was the possibility that something big was going to happen. So I'd give you a precursor. It wouldn't be telling you necessarily it's going to happen, but it sort of suddenly, normally you have a fairly high confident measure out for a period of time, and then the PDF gets really wide, suggesting that some kind of event is probable.
Yep.
We did something like that for grid frequency in the UK, because they were looking for the chances that a generator was falling off the grid. Cause in the UK, the biggest generator is like 8% of the total generation in England and in Britain. So getting an idea of seeing that go wide was telling you that some generator was about to fall off the grid, and that the same sort of thing, I guess.
I think so.
Any other questions?
This was really cool. I appreciate you giving a seminar.
Yeah, thank you very much.
Okay, my pleasure.
Otherwise, we'll see I actually don't know that I have any speakers. We still have about 2 or 3 sessions left. And the dates are a little bit wonky. I just had a trip come up that's coming up in 2 weeks. So I'll be starting to hound people, see if we can get some other speakers.
Please let me be aware of it when you do, so
Yeah.
that I
Yeah, for sure.
can get to see what people talk about.
Yeah.
Also, I'll advertise, I'm speaking at the business school on Friday. With the title, Why Do We Forecast? Which is sort of a slightly different focus, but the same questions, reasons, investigating while he's here.
Is that on Zoom?
It might be, I can ask them.
Oh, if it is, I'd love to listen in.
I'll CC you on my request.
Yeah, certainly. Feel forward the
Thank you.
invite to me and I can forward it around.
Great.
People in space kind of thing.
Okay. Thank you.
Yeah, thank you.
Thank you.
Take care.